Dr. Fizz here in theoretical physics with four vectors. Four vectors can be considered a generalization of three vectors. We live in a four-dimensional universe. We have x, y, and z, the three vector, and time has been added. Now we can't add t by itself because it wouldn't make sense dimensionally. So we make t a distance by the speed of light multiplying it. So speed of light times t gives us a distance, and then it's on an equal footing. Time has been placed on an equal footing with x, y, and z, thanks to that marvelous invariant quantity, the speed of light. So this is our four vector, and if we take the differential for the dx super mu, we get the differentials. This is the common practice, to use a superscript with a Greek letter when you have the four vector, and a superscript of a Roman letter like L, I, J, K, M, N when you are just talking about X, Y, and Z. So then you would have X super 1 is X super 2 is Y, and X super 3 is Z. Mu equal to 0 is your time coordinate, so you can reserve 1, 2, and 3 for X, Y, and Z. Then we look at another definition. If we have X sub mu, the convention is to make the spatial dimensions here negative. And when we do that, we can write down the ds squared, which is kind of a generalization of dx squared plus dy squared plus dz squared you find in calculus. But in relativity, we have the dx squared, dy squared, dz squared with the minus sign, and the c squared dt squared with the plus sign. In the old days, they would have another convention where it would be the other way around. Because when we started this class, remember we had x squared minus c squared t squared. But this is now the convention when you define the ds squared is to do it this way. This is still going to be invariant because as long as you have a relative minus sign when you have space and time, so x squared minus c squared t squared would be invariant. Also c squared t squared minus x squared. So this is the convention to set it up like this. Now watch this idea. If you look at two frames of reference, say a prime frame and an unprime frame, you basically do the same thing. But what I want to do is make the dx, dy, and dz in one of the frames equal to 0. So I just have c squared dt prime squared. All right. Now, when I do that, then in that particular frame that had no, let's say, deltas in x, y, and z, all of the ds squared is in the time. When that happens, we call that special dt prime, we call it d tau. That's called the proper time. That would be the time of a clock that's at rest, which we looked at earlier. And here is a nice little equation that relates the two together. So ds squared is c squared d tau squared in the frame where there's no spatial differentials. And then in general here we have the c squared dt squared minus dx squared dy squared dz squared. Now here's a cute little trick. Watch this. We will factor out dt squared and c squared from this right-hand side. Now we factor out the c squared from the first term, and the d on this here, the c squared and dt squared. The dt squared we're going to pull out to the right, and the c squared will pull out to the left. Then what's remaining is 1. And what happens here is you have to divide by the c squared you pulled out there and the dt squared. So each of these has a c squared. Each of these three spatial ones have the c squared and the dt squared, but this is neat because dx dt is velocity squared, vx squared, vy squared, and vz squared. So when you add vx squared plus vy squared plus vz squared, you get v squared, and you're dividing by c squared. That's neat. And you have the 1 minus, you have c squared out here, dt squared. And then if you are to take the square root, you get dt and divide by the c squareds cancel. C squareds cancel. Take the square root. D tau is the square root of 1 minus v squared over c squared. See, we mentioned how this keeps showing up, dt, and this is a neat differential form of your time dilation because, see, dt would be say me in the laboratory measuring that clock moving by, so I see a delta t, a delta x, a delta y, and a delta z, but that clock in its frame just has the d tau. See, so think of this as the differential form of our time dilation formula, where before we had this as a t and this is a t naught. So that's a neat little way to review time dilation and see it in differential form. Now we come to the definition of the derivative of the 4 vector, and that derivative, what time do we use to take that derivative? Well, Einstein said we should take the derivative with respect to the proper time. That is special. There's nothing more special than proper time. Everyone will agree on the proper time. It's the time of a clock in its own rest frame. So taking the derivative with respect to the proper time, then we use this conversion here for the differential. In other words, this d tau is equal to dt, all right, times the square root. So here each dt in the denominator is multiplying by that square root. So that brings us to this equation here, which tells us that you have here 1 times c for the first slot, and then vx, that's neat, vy, that's neat, and vz, and the 1 over the square root, which keeps showing up. That is the 4 velocity. And for the 4 momentum, what we're going to do, by the way, before we get to the momentum, just want to point out that you can write this as a vector. Some people like to do that, one time dimension, and this is like your spatial dimensions. This is a velocity. The velocity v vector and the velocity of light. Look at that for the time slot. And this shows up so much, we define gamma to be 1 over that square root. So we can write this 4 velocity as gamma c and v vector. That's cute. Then for the 4 momentum, we simply multiply by m, because in physics the momentum is the product of the mass and the velocity. This is our special 4 velocity that Einstein points out as being very important because it's a derivative with respect to the proper time. Then all you have to do here is put an m in there and you have the 4 momentum. So let's review these things and look at the 4 vector and the 4 momentum. And the length of the vector is obtained by the generalization using the Einstein's idea of taking the time, squaring it, and minus the spatial dimension squared. So just think of length like you would normally say, what's the length of a vector? Be x squared plus y squared plus z squared. But here we have 4 dimensions where we do c squared, t squared, and minus x squared, minus y squared, minus z squared. And that is invariant because in the frame where there is 0 for the x, y, and z, it's all in the time. And notice that when we do the same idea with the 4 momentum here, we want to, for the 4 momentum, take gamma squared, m squared, c squared, and subtract m squared, v squared, and the gamma squared has been factored out. And when we do this, the gamma squared gives you this 1 over the 1 minus v squared over c squared. M squared, c squared can be pulled out. You have a 1. And then here you have v squared over c squared. Notice that this cancels and you get m squared, c squared. This is very important stuff because what this is saying is that when you take the length of these vectors, every frame, doesn't matter what frame you're in, you get a constant. You get an invariance, m squared, c squared, or the proper time. Einstein was so impressed with this kind of thinking that he wanted to call his theory of relativity the theory of invariance, or the invarianten theory, the theory of absolutes. The laws of physics are absolutely true in all frames of reference. The speed of light is absolutely constant. The lengths of the vectors in 4 dimensions have this elegant invariance. So that is really, really neat stuff and a very elegant way to see some of Einstein's thinking.